we can start.
Okay, thank you. So with this, I cannot see you because I'm looking at only the presentation. So if you want to interrupt me, please shout out. Raising your hands won't help, unfortunately. Okay, because I cannot see you. All right. So intro. First of all, my name is Akara. I work for PayPal, and I'm a founding member of the Scoops project. I am architect for messaging at PayPal as well, but I'm still a what would I say, permanent contributor to Scoops. My friend Anil Gosel, who you will, if you follow Scoops, you will probably hear from him, is the project lead at this time. But there's no less focus for me. I'm still very passionate about the project. And today I am coming in and talking about streaming big. What I mean with that is we know about streaming architectures. I feel most of you might know about Akka Streams. And if not, please yell out. Don't raise your hands. Okay. I can go a little bit around it, digging into Akka Streams. All right. But then how do we make it big? How do we really make it production ready in PayPal? And I'll also talk about patterns, application patterns, how it's deployed, how it's being used. The trivial ones I'll probably just browse over. The non-trivial ones I'll talk about it a little bit more. All right. And finally, the open source side, I'll go over what we have to offer. All right. So let's jump in. Scoops, we call it the streaming machine. Okay, it used to be an actor machine before Akka Streams was there. I was fascinated by problems that that Akka solves before we started Scoops. Okay, and things that have not been solvable in the common environment. I had background, by the way, I have a 25-year, 23 years to be exact, background in Java. Okay, I did Java EE, I did Spring. This is my second framework that I did at PayPal, and it solves a lot of issues for us. So with the streaming, what does it mean? It means that Scoops is like a car, Akka, HTTP, Akka Streams is the engine, Akka Actors 2, okay? But Scoops brings it out as an end-to-end streaming machine, right? Where the back pressure that is provided, the resiliency that is provided by Akka is actually end-to-end, right? And of course, it is pure async. So that means that when you get into Scoops, you get right into streams. People start to ask me, how do I deal with actors? Or where are actors taking a play? Actors are great at containing state. Actors are great at interactions that have no predefined topology, unlike streams, which has predefined topology. Actors are a little worse at back pressure control. You can load the mailbox. Okay, so actors become a part of your programming model where you have to store state, where you have to go remote. Actor is very good for remoting. Okay, and everything else on the mainstream becomes now streams. So why do we use Akka Streams? Of course, we have proven that the architecture is extremely sound. Okay, it's high performance. It's probably not the highest performance thing that I can find on Earth, even in the JVM, let's say it this way. There's always very, very extreme architectures that I could find that might be faster. And if you are really trying to iron out the last bits, the last cycles of your processor, Akka is not that one, but it is very efficient. Okay, it is also very comprehensive. That's what other frameworks are not. They are not comprehensive. You have to combine that with other models, other concurrency models to make your application work. And people do make mistakes over there, right? It is reactive streams. Reactive streams is actually started by the Akka guys, combined with Netflix and a couple of other folks. right? And it is becoming the standard. What appeals to me from the Akka Streams is the what we call the graph DSL. And especially for Scala developers, I don't have an example here, but it's basically connecting the flow components together in a stream graph, allowing you to see as if it were a graphical view of what your system is doing. So any area that I'm going to talk about in terms of patterns can be modeled in a few lines of stream graphs in your code, right? That's what's appealing. And it's all type safe, it's all compiled, it's all safe, unlike there are many other technologies in the past that try to model it in XML, and then it gets processed at runtime. You have errors at runtime. This is all safe, all right? As safe as it can be. I mean, we can argue about that. And it kind of unifies the pipeline processing part. Now, people would say, are we only there for kind of pipeline processing? Yes, I would spot, but we can do everything. You can think about just about any problem as streams. You can think about the universe as streams of information, streams of events coming in. And that's exactly where we stand. We process those streams. We ingest those streams. All right. So going next to operationalization. All right. This is more of the basics to say, what do we need for operationalization? First part that we focus on is the service lifecycle. Usually when you are in a scale like PayPal, you are not talking about a service of 5 systems. We are talking about 20 systems, 30 systems, 100 systems. I have extreme cases of 3,000 systems, right? Thank God it's not Scoops, all right? So we are much more efficient than that. But they come in big flocks, right? And we have to integrate. Systems get upgraded, get redeployed at any point in time. Those are part of daily routine. Okay, even recovered, the cloud is not stable. So you have to take a node down, get a new node, deploy the system again. You know, you have to do that reliably. So the service lifecycle comes in very handy. Okay, it is part of the key constructs. Manageability is the second part. And resiliency. How do we make sure the service keeps running? Any interaction with you, from you with PayPal, is actually revenue generating. And whether you know it or not, in one way or the other, it contributes to the revenue. So any failed interaction is lost revenue, right? Even if we go with 0.01% failed interaction is a big deal. So system reliability, resiliency is key. I'm going a little bit over the lifecycle requirements on this slide, talking about first, what is it, right? So we need to have a state model for the service lifecycle, right? We have to be able to observe that state model or the current state, internally and externally, right? And basically, we have to manage the transition without data loss. For streaming architectures, that is the key, all right? I mean, an async stream, if you break the stream in the middle, you can say, okay, we can always restart, redeliver, but that means that you are assuming idempotency. And for any new application, I would assume that you think about idempotency. But if you go back in time, not too long ago, most of the services that we have in PayPal are not idempotent. So if during the stream you make service calls, those might not be idempotent, no matter what conventions we say it should be, right? So data loss is becoming an issue. Manageability, this is kind of a checklist slide. So I'm not going to talk about it one by one, but you can just go down and say, these are the things that we do, and plus much more, right? And anything that goes through production will have to have all of these available to us, okay? Big deal, right? And resiliency. Resiliency is about anomalies are more common than not, right? Spikes, load spikes that are 10x the normal load are not uncommon. Okay, so we of course do have the end-to-end back pressure from Akka Streams, but on top of that, we need to build resiliency ourselves as well. In terms of timeouts, we have a part of the stream that might access certain resources, and that resource might not be available or might be slow. What do we do with those? Retries, they might return errors half of the time. We have to retry half the time. That would be extreme, by the way, but we have to be able to retry. And unfortunately, retries will get the stream out of order. Akka Streams is generally in order. There are certain stages that are out of order often, okay? And circuit breakers is a very, very advanced version of timeouts, which says if you time out or error up to a certain pre-configured count, then I'll turn you off for, let's say, a minute, for a certain time, okay? And say this resource is not available for a minute, and that minute or that time is configurable. Then after that, it basically comes back and say, let's try again. Are you back? If the first try you are not back, I put you on another minute of timeout. Okay, this is reducing the error rate, and especially in some cases, the downstream service is not giving us an idea whether it's giving me a response, it causes timeouts, or basically it might not be timing out, but it'd be slow. You know, those kind of things can be caught by the circuit breaker. And while it is playing less of a role in streaming architectures as opposed to normal Java EE/Spring architectures, it is still playing a big role here, big enough. Okay, so it's part of our offering and part of the infrastructure. Life cycles. I'm jumping back and forth here. So here is how we do the lifecycle part, right? These are the 4 stages of our life cycle. Starting, active, stopping, and stopped. Most of the time, a good service is going to be in active state. Before it comes to active state, it's starting. And when it's active, we can tell the load balancer, saying, I can take traffic now. And that's what we use a construct called ECV, or extended content verification. Every load balancer is slightly different, and every organization is different. So the ECV part can be done through our admin console, for instance. But if you want to write your own admin console, actually, we do have a separate one for internal use. That is up to you. It's all drop in, by the way. Okay. There is from message consumers. You are a Kafka consumer, a JMS consumer. It's all starting when things are active. When every part of the system is initialized, then we can go in and say, okay, let's start opening the pipe and get the messages coming. Now, when it goes to stopping, it has to stop the pipe, but it has to keep processing the rest until it's done. We have to have a way to check. And we have got a construct called perpetual stream for those kind of cases to reliably shut it down. And that's exactly the hard part of this. Okay. Jumping into streams a little bit without really using this Scala construct, which looks very similar to what you are seeing here. This is a simple service, okay, that takes a stream of requests and puts out a stream of responses. In this case, the model is HTTP. It doesn't have to be, could be anything. And this is a common set of stream components. The first one doing unmarshal, then you validate, and then you start processing, and you make a client call. Usually our services make multiple client calls, right? So it makes another set of calls going out, and then it filters and processes the responses coming back, going to formulate the response, and then we go to the marshal stage, where it basically puts the response on a wire and putting it out. So this is how an HTTP-based stream looks like, right? And this is what it looks like for the application. Now, let's jump into some of the architectures of how we make it really resilient, okay, and make it manageable. So going to this slide, you can see, I'll jump back and forth. We are moving this whole picture to the right, by the way, okay? And before the request comes to the unmarshaled stage and after the out, there is something that the infrastructure adds to it. It's called the pipeline, okay? The pipeline is something that usually your infra team, this is all pluggable. So you take skills, it comes with some basic pipeline components that is in skills already. An application can modify, but the infra team, and that's part of our team that I'm working for, is actually defining what needs to be in the pipeline of every application by default. So that's the default pipeline. And this is, for instance, request comes in, application doesn't want to deal with logging. That's kind of a system concern. So logging that the request has come in, and then monitoring, it goes and updates all the counters, updates the TSDB, time series database, that says, okay, there is something new coming in, okay, so that we know we are actually taking 3 billion hits or 4 billion hits or 5 billion hits that's coming from monitoring data per day, right? And then security comes in, saying, I need to authenticate and authorize that this request is actually legitimate. If not, these pieces will just return the response out, say, oh, I'm sorry, you are not allowed. And as you can see, the pipeline is built of a construct in Akka Streams called BD flow, which is bidirectional flow. They have got 2 input ports, 2 output ports going opposite directions, and you can stack them up. This is really an Akka construct, and when you put them together with the rest of the flow, Akka Streams has got something called fusing, which basically makes this ultra fast. Okay, instead of putting each of them into a separate actor and having to cross async boundaries every time, it merges them. The jitter of latency is reduced dramatically with that. So when you are dealing with a system that needs, say, 50 millisecond response time, that might be low, but 50 millisecond response time at 99.99th percentile, that's pretty good, okay? We have achieved that, right, with this architecture. If we went to actors directly, we might not achieve that because there's sometimes too much going on in terms of crossing async boundaries, crossing actors, and every time we put it into a queue, we don't know really how long it will stay in that queue, so the jitter will be much greater. And in a similar sense, on a client side, when you make a call out, we provide HTTP client, which is based on Akka's HTTP client, from Akka HTTP, but we put the pipeline architecture in front of it. It's exactly the same pipeline architecture as we do on the incoming side, right? That allows you to log, to monitor, and do many other things to your request before it goes out. And again, just to reiterate, generally, the pipeline belongs to infra. Okay, applications might optionally want to add their own pipeline handlers. And you can think about, if you are only familiar with servlets, you can think about it as a servlet filter. But the servlet filter doesn't take care of the outgoing path, right? So the pipeline can be used for both sides. All right. And the nice thing is it totally fuses with the rest of the stream, with your application, without your knowledge, without you seeing it. Again, these are manageability concerns generally, okay, which gives you the logging, monitoring, even authentication and authorization. Or if somebody hits our services with a DDoS attack, there are some gates in there that we can use to identify a DDoS attack and say, I'm going to shut this off, right? So all of these can be done at the pipeline level with minimal cost. With that, you saw the pipeline usage. Let me introduce a concept that is built on top of BD flows, right? We call it stage gates. And a lot of our resiliency components are coming in the form of stage gates. So a stage gate is a gate that separates a flow from another flow. It's in global terms the same flow, but you put a barrier in there. Okay, and that barrier can do many things. The stage gate itself, being a single media flow, can contain synchronous internal state, which means what is on the outgoing side, incoming side, and outgoing side is all in sync. If you say, let's say in a circuit breaker, you break the circuit, you see that the error rates on the incoming, on the outgoing side is too high. You break the circuit, it breaks it immediately. Okay, it's synchronous in that sense. So you can place them into the pipeline. They are the same constructs, but you can also use them in other places. To make a picture out of that, it's basically this picture saying you have a main flow and there are some resources that you access in your gated flow, right? So you put your circuit breaker in the middle between the main flow and the gated flow. That gated flow would be, let's say it is a more risky thing. You have to access, say, a remote database or a remote resource or a service sitting in a different company, okay, from that gated flow. And we know that it can error out. That company might not be available. So circuit breaker is basically saying if I get enough errors from that gated flow, I will just stop it for a certain timeout, right, as I said before. And just to go through it quickly, these are the common gates that the monitor gates we don't provide, but it's a common idea. But all the other pieces are provided. A timeout is a short circuit that says if I don't get a response in a certain amount of time, I'm going to send a timeout error down. But then I have to consume the response. So there are some difficulties in implementing these. We know they are challenging to implement, and therefore we do it for you. Okay, and it takes us a lot of time to do these kind of things. Retry components is the opposite. A response comes in, we deemed it being an error, and we go retry. Okay, before we send it back to the main flow. We are actually currently doing major surgery on the retry component, making it even more efficient. Not that it was not good. It is being used in production very successfully at this time. Circuit breaker, I talked about that too many times, so I'll just skip that. And monitors are just like, I really want to know what kind of lag is in the subflow, or what's the message loss in that flow, what's the in versus out ratio. Any monitoring, any counters that you want to put in the monitor comes in form of a common gate, right? Because you have to check the in and out of it. So with that, I kind of give you an idea about how the components and the operational requirements are being met. So we can actually even get to handling very large number of transactions, right? In the next part, in the next couple of slides, I'm going to talk about common application patterns. And let me just be straightforward here. You will probably ask me, can you do microservices? Yes, okay. Can you do message-based microservices, JMS-based, Kafka-based? Can you do badges? Yes, but I'm not going to put that into application patterns. They are just too straightforward, right? So it's just a stream of requests coming in or a stream of messages coming in, and you just go and handle those in the stream. It's very suitable for all of these, but it is much better than that, all right? So what else can we do with streams that normal microservices or other service architectures have a hard time? Things that span multiple messages or multiple requests. For instance, many of our use cases group let's say it's better to make a service call with 100 requests or 100 data points putting in at a time, instead of making use or making 100 service calls. Okay, it's much more efficient. So you can use streaming to batch them up. Use a group by, group within, or grouped construct in any combination of those to group multiple messages together. Group within is good. It has a time bound. Let's say if you say anything that comes in during this 10 milliseconds, I'll batch it up and make one service call to resolve all of them in one shot. That's another very good use case for streaming patterns, right? So I'm just talking that through. I don't have, it's very hard to picture that. It's better to explain, but let's go to the first pattern that is very common. So one of the use cases, common use cases, are data collectors, big part of the data pipeline, right? So for instance, you are getting data through HTTP coming in. This also exposes some of the Akka Streams and Akka HTTP architecture, saying that each connection that you get is its own stream, right? So each connection will have its own request coming in, extraction stage, instance. It's looking the same, but it's multiple instances, multiple, in Akka Stream terms, we call it multiple materializations. And if you handle 5,000 connections, you have 5,000 of these. We have this component that can dynamically take data from these streams. And meetup is actually part of the Akka Streams components. Very good piece, right? That says, you can see, I'll try to use my mouse a little bit. We have this junction point saying, a request comes in, we need to go to make it respond. But there's also something called also to, which is represented by this junction point here. And it also to says, send a copy of this after extraction to the merge hub, okay? As a new connection is created, another stream is created and another port in the merge hub is created. It's dynamic. And as a connection terminates, another port goes away. That's the power of this. And that gets everything onto a single stream. The stream is dealing with concurrency by itself. So usually you don't have to deal with concurrency at all. The nice thing about doing this is forget about synchronized, forget about most of the Java util concurrent constructs, even the Scala concurrent constructs, besides timing, timeouts, and those kind of things. Anything that goes across threads, you basically should avoid in this architecture, in Scubes and in Akka altogether. So use Akka concurrency constructs. Now, that goes to merge hub, and it goes to enrich. What we do there is up to the kind of data. You might have to make sure that the data points that you collect have some meaning, and that's what the enrich stage is doing. You send that enriched data down to a Kafka sink, an open source piece coming from the Akka Streams Kafka project, right? That now writes to Kafka. Okay, how you configure your Kafka? Sometimes we provide plugins in Scubes, like internally we do so, just to standardize the way that you configure Kafka, right? But finally, what you are dealing with is the real open source component. We try not to hide other open source components or wrap it or modify it. We try to expose everything verbatim. The next pattern, very, very common also for microservices, and this is a rather simplified view of that, is a stream comes in, you go to unmarshal, and then you basically call service A, service B, service C. Okay, and these are all of these in this model that you see, it's in sequence, but most of us are not dealing with it in sequence. It might be that you call A and B. Okay, once both A and B are done, you want to merge that, do some processing, and formulate request for C. Pretty low. Just that's what fits on my slide. Okay, so n number, you can create a graph, and if it gets very indeterministic, And we have got some use cases where it gets extremely indeterministic. Infrastructure in Scoops called the Scoops orchestration DSL, which uses composition, more of an actor model. So you can, from your stream, you jump into the orchestrator, and that using a map async usually, right? The orchestrator will then call services if you don't have to a preset topology, or the topology can change a lot, right? And come back. So we have got two facilities, and the use case for the two facilities are somewhat a little bit overlapping. In general, I recommend streams doing that, but whenever it gets difficult and whenever it gets complex, the orchestrator is doing a slightly better job over there. Okay, especially when the topology cannot be totally predefined. Pattern that is actually one of the ones that takes the PayPal is data gateways. And here I'm talking about only data collection, but actually that data gateway is two ways. Drawing that is going to be much more cumbersome in this slide. Just to give you an idea, you have a data gateway that takes multiple sources. One source is your HTTP source, which is a request coming in, right? Another one is a Kafka source, and we might have other sources from multiple places. Of course, the HTTP, because each connection edge is its own stream, you need to use a broadcast in stream graph concerns, and also two in language concerns, right? To send merge hub. Okay, that merge hub basically does the merge of all the dynamic streams coming from Akka HTTP, and the Kafka source here delivers things directly, and it comes to a merge point. In many cases, we do not know where to store the data. Let's assume, let me label it, for instance, store one might be HDFS, the object store, okay? Store three might be just sending it down a Spark pipeline, for instance, right? And so forth. So you need to have some metadata that configures where should I send that request or that data point. So you go stream through the metadata client, which then, in a sense, enriches your data elements with information saying this data element should go to store one or to HDFS, right? That data element comes out of the stream, right, and goes to a partition stage. Partition is a standard Akka Stream stage, okay? The partition stage takes a function and then routes the data to the right data sink on the first store and the second store. So this is yet another one that is hugely used, okay? And we have got so many variations of this, right? There are some other variations, micro batches that we do, which it's very hard for me to put on a single slide like this. It's a more complex architecture where we split large batches into smaller streams, smaller batch streams, okay? And we process them end to end. So in that case, we store it in a intermediate store like a database, and we stream the data out of the database. That's one use case. Okay, that is also very beneficial, has gained a lot. So you can see that almost every stage could be its own microservice, but by consolidating, oh, I'm sorry to say that, it's, I hate this term, but there is so much nano services around, services that do way too little, right? And we wanted to make them more efficient by putting them into a pipeline. So by doing so, we gain a ton of efficiency and cut down number of services. Of course, it might go against some philosophy saying, hey, we should break it down and we should go microservices. But if I give you a data point for PayPal, PayPal has got about 2,500 nano services in my context here, right? And if you have got 10, Yeah, by all means. But if you have got thousands, they become unmanageable. So that's a whole different topic that I can talk about, is a path we shouldn't go with services, right? So this is a good consolidation and a very, very efficient way to model and to execute your stream and everything. I mean, even request response, even CRUD operations can be done using this architecture. Yet it is not a strong point. So I'm not going to talk about that. CRUD is just basically a request coming in gets translated to a storage, or request coming in gets translated to a query, and with a response going out. Those kind of operations are just very simple ones, right? In the invite of this talk, there was a reference to my talk 2 years ago about crawler. Okay, so crawler is one that doesn't meet any of these patterns, but it's still worth mentioning, right? So crawler is a batchy application. It's a online batch, but it could run for very long. So what happens is we stream the request saying, I have these URL entry points. Okay. Every time it comes in, we say, did we really already have data about this entry point? If so, skip. Okay. If not, go and download those. This is just a web crawler, think about it. And the process is basically trying to break down and see what kind of links there are in the page that we just crawled. Okay. Now, the problem set with crawler is that one entry point can split into 10 other entry points. So we come down and we store those entry points. We send the page to our backend big data analytics system to do whatever, which I don't understand. Okay, what exactly our data scientists are doing over there. But then for the links that come out of it, because it's 1 to 10, 1 to 5, and so forth, it grows exponentially, right? And if you want more detail on this talk, please go back. I ask me, or you will find out it's on YouTube. There's this exact talk about crawler on YouTube already, so feel free to just go and watch it. Okay. Then those URLs get stored to Kafka. These two ends are actually the same Kafka instance, and they come back and go through the process again. URLs might not be unique, so that's why we have to cache. And if it's already crawled, we are not going to crawl it again. Okay, this is more of a blacklist cache or whitelist cache, basically. Oh, I'm done with that already. And we tend to use things like Couchbase for this with a TTL to allow that entry to expire by itself. Okay. Yep, that's what it is. So now I've got about probably 5-6 minutes left. I'll just quickly go talk you through Scoops, what it is, and how you get access, and how you can work with us as well, right? So let's take Scoops under the hood. Okay, meaning that of course you open the engine. It's an Akka Streams engine sitting behind it. Okay, we provide the wheels, we provide the chassis, we provide anything that allows you to drive it easily, right? And the gauges saying, are you overdriving it or not? So we provide the bootstrapping, the lifecycle management, right? We provide the module system. This is key because all the enterprise integration is dependent on the system. The integration with your own monitoring system, your own logging system, your own controls are all through this loosely coupled module system, which is not part of the core application. By declaring a dependency, we usually do it using templates. If you use a PayPal template, you have got all these dependencies preloaded for you. And that kind of gives you out-of-the-box operationalization while you still code to open source. Okay. So, and all the integration hooks are there. Okay, and even for monitoring, we have got like we use Coda Hail generally, and allows you to adapt your Coda Hail to your monitoring system directly instead of trying to just do it as Scopes hook, right? Which is pretty standard then. Console, we have a JSON console, which is very human readable, but also very machine readable. So that's if you want to integrate your monitoring with the console, you can do that using JSON very easily. Okay, we have got clients that, as you saw, with a pipeline and with a concept called resolver. The resolver is very important because when you talk to a service, say a payment service, right? The payment service in your dev environment, QA environment, sandbox environment, production environment are all different places, but you don't want to write those if statements into your application code. That's where the resolver comes in and say, okay, give me a link or a client that talks to my current payment service, for instance, right? And it's pluggable, so you can, as an organization, write all your resolvers. Test tools, all the goodies, all the great stuff on Akka test tools are part of this offering. Plus more test tools that allow you to test in this container mode, right? And making it easier to test your application, not only saying, here is my route and test my route, but I want the whole application to be instantiated for this. And all the actors, all the streams that are part of the application to be, or you can scope it basically, to be instantiated and tested more like, almost like an integration test, but we do it in a unit test fashion in CI, okay? So other goodies, as I mentioned already, we have templates, we have got programming patterns and orchestrators and so forth. Please feel free to look it up. And we also are a supplier of stream components that you can make use of without even using the Scopes core. So these are the list of the components. We talked about circuit breaker already, dedupe, timeout, retry. There is persistent buffer. That's an interesting case. We have customer requirements to say, oh, Kafka sometimes rebalances, and it takes some time to rebalance. But I need to be able to store the data flowing in before going to Kafka. Okay, and usually I shouldn't store anything, but if Kafka rebalances and goes away for a minute, I don't want to queue it up. I don't, because our data rates are humongous, right? I want to be able to quickly write this to disk. So the persistent buffer, broadcast buffer, those are the components that you can just put in the stream, a buffer component that actually has a disk backup, right? So let's quickly talk about what's next. We are actively working on Scopes 0.10. I call 0.10 a 1.0 M1. Once we get it out, the API is unlikely to change. Okay, very few features will be added between 0.10 and 1.0, but it's more like a proof of concept of 1.0, and we want to iron out all the kinks before we actually put a 1.0. It's going to be based on the latest Akka 2.5. Well, I don't remember what is latest today because they release pretty often, and Scala 2.12, and then the latest Akka HTTP, right? Documentation, you can find it, link very soon. More components, more goodies, okay? The programming patterns or application patterns that I talk about, I haven't committed to that, so don't take it that way as is just yet. But we are trying to take some of these patterns that are common and put them out as templates as well. Okay, so you basically want a data collector, you use the data collector template, you get it out of the box, and then you just go and add your components that you want to use for processing the data, right? Monitoring, we have improved the monitoring greatly between 0.9 and 0.10, okay? And what we have signed up for is tracing. We do tracing internally to a certain point, but tracing is always an issue in asynchronous architecture. So we will put our focus on that and really make sure that open tracing, there is a standard called open tracing. Open tracing works well with this architecture. Okay, that's actually a request that came to us from the open source community and got a pretty good amount of weight. But also it's one of these research items that will take quite a bit of work to get right. And what's beyond Skills 1.0? Well, Akka has always been dealing with distributed systems, right? We are a little late in that game, actually. Most of the systems that are, we do have a couple of use cases, and we have got a lot of demand to go support distributed systems, but it might not be something that I want to jump on very quickly, because distributed systems are inherently complex. So we need to make sure that we can operate it at the scale that we are running. And also the infrastructure behind it, the path layer, which is totally out of scope, has to support stateful systems or distributed systems, which is still a challenge. Okay, so, but we are moving there slowly. See that probably by late this year, we will start to expose certain distributed patterns that are not costing us in terms of handling large scale traffic, but are helping us. So we are very careful on those. All right. So in summary, under the hood is Akka Streams, Akka HTTP, okay, which provides resiliency, right? And what we add is operationalization. We add patterns, okay, and we basically look at real use cases inside and outside of PayPal. And one of the philosophies is anything that is not PayPal specific, anything that is not an integration between things that I cannot open source in PayPal, will always go to open source first. We do not have a separate Skills repo internally. We work directly off the open source repo. Okay, so anything that you see in the master is what we have committed last, right? And we are actively contributing to that. We want to make sure that there is no sacrifice on performance because of us. Okay, so anything that comes out of Akka Streams and Akka 2.5 is even better. It's even more performant. We want to make sure that we live up to that and not add any overhead. Okay, that's pretty much what we provide, and that's how Skills is mainly used nowadays, right? So with that, let me end this. Definitely, I'll switch to a view that I can see you guys so that you can raise your hands. Okay, but there is the website github.com/PayPal/Skills. On that one site, you have a badge called Join Chat. Get a Join Chat. Hit that, and then you will be able to talk to us. Come say hi. Any discussion, any questions, I have an address here. Please feel free to go to Join Chat and talk to us. And if you are interested in following us on Twitter, these are the two addresses at Skills, and for me, myself, at @Akara. Okay, we are not noisy, so I'm not going to spam you on Twitter. Okay, so feel free to follow us, and I'll also follow interesting people, try to retweet interesting stuff, but never spams. Okay. All right. With that, I'll open up a Q&A. Let me switch to our view of the team, the room. All right.
All right. Thanks, Akara, for good overview of your Scopes framework and especially the
all right
pipeline. That sounds interesting. So let me just ask, maybe we have some questions from the audience first.
Someone wants to ask, just raise your hand. I'll tell you your question.
Okay, we have actually some questions in our online.
Absolutely.
Okay, it's actually one from me. How do you design Akka Streams in general, and is there like a test first approach when you're starting implementation, like similar to TDD?
Okay, I would say I'm not a, while I'm practicing TDD to a certain level, I'm not a huge fan of TDD, but what Akka Streams provides you is a very high level view of your application. So when now you think differently, right? You think about stream components and how you connect the stream components, right? So I would start with designing the functionality. Okay, when I do components, yes, we are very TDD oriented. We know exactly what the components need to do, what's the input, what's the output, and we test those. We often define the test before we define the code. But also, I would say the opposite is true. We kind of prototype it first, and then we define the test. Nothing goes in. This is a philosophy that if you get to contribute to skills, you know that everything has to go with a test. Actually, I don't know. I don't really personally care whether the test comes first, but the PR has to have test, has code, has documentation. Right. So, but the whole system, when we start designing it as a whiteboard, right? And the nice thing about this architecture is that whiteboard pretty much translates to your code, your stream topology, one-on-one. Okay. That's what I love about this architecture. The view is not like, oh, I have to translate what's being on screen into code. What you write on screen or on the whiteboard, you translate to code directly. That's how we think about that. But it is a different thinking.
Okay.
Right.
Thanks. Another question: is it necessary to know functional programming to use Akka Streams efficiently?
I would say you don't have to be deep in functional programming, but you have to adapt to the paradigm of functional programming. Okay, so things like high order functions has not been there in old Java. It came in Java 8. Of course, it's prevalent in Scala. But do you need to know the whole type system? Type system is the most powerful part of Scala, but also the most complex part of Scala. You don't have to know most of that, right? Most of our users that use Scala actually don't fully understand the type system, but they understand how they write code, and they understand how high order functions work. Okay, and that's pretty much what you need to know. You don't have to be a PhD in category theory or something like that. No, not at all.
Okay, it's a good encouragement.
Great. Yep. Trust me, it's not hard.
Okay. Another question. Can you compare Akka Streams with other approaches for maybe solving similar problems?
Okay. Can you name the other approaches you want me to talk about?
Unfortunately, the person who asked this.
What are other possible approaches in general?
He was asking. Did you hear it?
No, I didn't hear it.
Okay. What are other approaches in general? I mean.
Okay. Let me talk about this. So before I started this project, I was working on a Spring-based framework. So can you solve this problem with Spring? Potentially. Okay. What does Akka in general provide you? Is a better defined concurrency model. Okay. And a better way to handle micro batches or batches of messages, or collecting messages across requests, right? So to do that in a traditional model, you need to go out of the system. I need to stick my data elements into Couchbase, for instance, right? And doing so, while it looks natural, it actually increases the complexity of the system. In some cases, you really want persistence, and that's worth it. In other cases, persistence is not needed, right? And just going out of the system, calling a database is a huge overhead. So can you try to solve the problem with a, let's say, a Spring traditional architecture? Yes, I mean, there is really no system you cannot solve, no problem you cannot solve with that. But in most cases, and I can talk about recent success stories. There is a blog post. If you ask me on GitHub, I'll give out the URL for that blog post from one of our use cases that solve it by saying, no, I'm not going to do it that way. I'm going to do it with a stream stage, right? And they gain huge efficiency and huge reliability. So yes, you can use you can solve every problem in assembly because every code translates to assembly in essence, but it is much more difficult and the modeling of it is not good. Also, on top of that, the efficiency. People go 10 different ways of trying to solve their problems and trying to help. Part of my job is to support our teams, and including you, if you come online, to successfully do your work, right? So it becomes very hard for me if people go 10 different directions. This is basically a framework that says, no, we have got a unique way of solving the problem, and I understand team, and we know exactly how to make you fly. So yes. There is yet another angle to this. There are a lot of other streaming frameworks around, namely like Java, Reactor, and those kind of things. And there are a lot of high-performance, very, very high-performance frameworks, and that's exactly why I'm not saying this is the highest one out there, like Almax, like some ways of using Aaron, although I see Aaron more of a transport. The problem with that is they are not comprehensive. Okay, meaning that you have to go, they don't provide you the whole paradigm. You have to go out and do the rest that they don't provide by your own means. And the lack of comprehensiveness is actually killing most of our customers. You might want to jump saying, oh, Almax is the fastest thing on earth. They do 5 million transactions per second on a single processor. For instance, I'm just throwing out the numbers, but that's roughly the numbers we are talking about. And so my application, when I use Almax, my application would also do 5 million transactions on a single CPU. Guess what? Nobody has come close. You really know, you have to really stick to those very low paradigms to make that happen. Okay. And what Akka Streams and Akka provides you is a relatively comprehensive paradigm, solving most of your concurrency and distributed processing issues. And that's what I love about it. And keep you in the paradigm without leaving too many gaps there. Okay, so that would be my answer to compare it with other streaming systems. And also, when you deal with complex streams, Akka provides you the component model abstraction, which other streaming systems don't provide you. So spot benchmarks, I have heard a lot that says Akka is not the fastest. But when you build whole systems, I've got huge success with making it a comprehensive offering that is fast. Okay, doesn't mean that you cannot build anything that's totally faster than this, provided that you really know what you are talking about. But this is supportable from my point of view. Right.
Do you have more time for one more question, or?
Let's do one more question. Okay, and any other question, go to our GitHub channel. I'll answer them over time. Right. Sorry, I don't hear you anymore.
Just a second. We have one more question. Can you say approximately estimated requests per second per server for typical high-load applications, which needs write something to a persistent storage?
Oh, that's a tough one to answer. It has got too many dependencies. So let me evade the question, but give you an answer anyway, right? And give you examples why I cannot tell you. Okay, a benchmark application that runs HTTP, for instance, I can handle about on a two CPU? Yes, 2 CPU system, and that's also subject of which 2 CPUs, but just as a reference, just throwing out, I can handle about 100,000 requests per second on a full-fledged benchmark application. You throw down HTTPS into that mix, that throughput comes down to about 7,000. You do Kafka consumption, we can do about 3 on a 2 CPU box, actually. We can do about 300,000 messages per second. Okay. Now, it will be constrained by the lowest performer. So when you throw in a database, it depends on which database, what configuration, but let's say it is common for real applications, our real applications, to run in the thousands of TPS. Okay, this is including I/O, including all the complexities, and including the biggest drag is PayPal's own operationalization and HTTPS or encryption. Okay, all of that is part of it. So that is not hard to achieve at all, getting into the thousands, right? Now, you might say, oh, I can do 1,000. Yes, I've been doing 1,000 TPS with SpecJ Enterprise and all kinds of things, but those are benchmarks. I'm talking about real applications, and getting into thousands with all the baggage that applications have to deal with in order to integrate into an operationalized environment. It doesn't work easily. Okay, so that's kind of all I can tell. Of course, we have to look at the use case, we have to look at the complexity, and it's very easy to take even the best system and put it on a crawl at 10 TPS. That happens too, right? You misconfigure certain things, it doesn't fly. So, but anything that you want to do, feel free. We are open to business almost 24 hours. Our team is spread between time zones in the US. So we will surely get back to you within a couple of hours. Okay, when you ask questions. All right.
Hey, Akara, so thank you for your time, and yeah, it was a nice talk.
Thank you. Thank you. And have a nice rest of your evening. Okay.
All right. Have a good
from your round.
morning. Yeah.
Take care.
Cheers.
Bye.